Hey guys, in this video we're going to talk about two-dimensional motion. For two-dimensional motion, we're going to be using our compass. So, let me see. So, we're going to use our compass points. Like, for 2D, we're going to imagine like we're looking at it from like a bird's eye view. So, we all should know our compass points. But if you don't, we have north, east, south, and west. And this is what we're going to be using for our problems. For this video, I'm going to be discussing like displacement because that's usually what you're going to be talking about when it comes to 2D motion, like this. So when you have something like this with 2D motion, you're going to get things represented by vectors. So our displacement is going to be represented by a vector, and a vector looks like this. The longer the arrow, the bigger it is in magnitude. You're going to have a direction. Well, our direction would be in between here. And let's see. So if we had this, I'm going to say this is 55 degrees, okay? Now, this starts at the E. We're going to say 55 degrees is here, okay? Now, if we go, what's 90 subtract 55? 35? Yes, 35 degrees. So using our laws, we know that this here would be 90 degrees, and 90 subtract the 55 would be what's on this side, which is 35. So to explain what this direction is on points of a compass, we would say it's first going east because this here is being connected to the east, right? So it would be east 55 degrees because that's this direction, and then the second direction, which is this one, south. Now, we could, if we wanted to say this the other way, because there's two ways you could say this. We could, for this vector here, we could also use this angle, 35 degrees. This would be, we start with the south this time because it's connected to the south here. This would be south, 35 degrees, east. East 55 degrees south and south 35 degrees east are the same thing. They're pointing in the same direction. They're both describing the same vector. Oh yeah. When we're finding the displacement, you're always going to add your vectors from the tip to the tail. We're going to get into that in an example to show you how that looks like because I want to. Now, let's say a person walks 5 kilometers east, then 4 kilometers south, then 8 kilometers west. What is their displacement? That's the question. I'm going to show you how you can find that. So first, like I said, you're always going to use your compass points. The first direction is, we're going to write down the directions actually, because first direction is 5 kilometers east. The second one is 4 kilometers south. And the third is 8 kilometers west. Okay, so we're going to do this on our compass. It's going to look like this. Now, your first vector is 5 kilometers east. So we're going to go east, and we're going to say that this is just your first vector. This line here, because it's east. And it's worth 5 kilometers. The second one, actually maybe I'll write east too because we don't want to get messed up. The second one is 4 kilometers south, so never eat sour watermelon. Go south, so that'll be going down 4. So 4 kilometers south. We're adding them the tip to the tail. Right, so 4 kilometers south. Now, when we're adding these never change directions. See, this here is still going south. This is going east. We're just adding them like that. We're not changing anything. Now we're going to go 8 kilometers west. This is west. Again, we're just going to add the tip to the tail, and we're going to go 8 kilometers. I don't know if that's how that works, but yeah, because there's 5, yeah. So it's going to go into here. It's going to go about here. And this will be worth 8 kilometers going west. Okay. That's how we're going to set up our problem. We want to find the displacement, which would be this value here. from tip to tail, right? So from the tail of the 5 kilometers to the tip of the last one, the 8 kilometers. Now the distance of this would be pretty easy, right? We're just going to measure how far he walked. 5 kilometers, the 4 kilometers, and the 8 kilometers, which would be 17. That's actually pretty far. My bad, but that's okay. But if we wanted to find the displacement, so this line here, we'd have to do a little bit more. So the first thing I would do in this situation is write out the values we know. So using this triangle because this would be this line here and our lines here to make it a bit easier on ourselves. So we're going to go like this. This line here is worth 4 because of the 4 here. So this would just be 4. And we know that this whole line is worth 8 and this part of the line is worth 5 because of this one up here. So the rest of that would be the 3 and the 3 would be here. So this side is worth 4 kilometers and this one is 3. Now, I'm going to erase this so that we have more room, but don't erase that, that's your work. And we're going to use the Pythagorean theorem because it's a right triangle and we want to find the hypotenuse, which would be our displacement, which is, I think, is really cool because it basically just means that the world is triangles, which is kind of neat. So we have this here, that's worth 4, and this is worth 3. Let's see if I can do this. Huzzah! A squared plus b squared is equal to c squared. You know, if we have trouble with this, maybe I'll make a video on like triangle laws and stuff because that might be helpful for some people. So 3 squared plus 4 squared is equal to c squared, which means 9 plus 16 is equal, well, the square root of 9 plus 16 is equal to c. And that is, what, square root of 25? That does not look like a square root. Is equal to c, which means c is equal to 5 meters. Okay, so our displacement is 5 meters, but displacement is a vector, and vectors include both magnitude and direction. So now we have to get our direction. Now if we look back on how we drew our compass, I'm going to redraw mine because I don't have it anymore. It looked like this, right? So this is what we just calculated. Now we want to find an angle so that we could get our direction. I'm going to do this angle here because we have more stuff. So use this angle here. Now we're going to use SOHCAHTOA because it's pretty great, and we know the values of, see, look, okay, so that would be this here is our angle that we want to find, and we know the values of O and A. So using SOHCAHTOA, we're going to use tan because we know our opposite and our adjacent. So using the formula, here, let me like, okay, using the formula, tan angle is equal to, holy crap, don't mind what's going on in the back of my video. I have no idea what they're doing out there. That is messy also, so remember to write that. Tan theta is equal to op over adjacent. Okay, so using the information we know, we want to find the angle, so we're going to bring that out here. And then this will be inverse tan because we're bringing it to the other side. The opposite is equal to 3. The adjacent, well, the adjacent is equal to 4, which means, I already did this in my calculator, but put this in your calculator and you'll get the angle is equal to 37 degrees. You're going to round it off to the nearest degrees because we don't usually do like points when it comes to degrees. So now we have the degrees and we have our displacement. Now, to write it all together, we're going to say the displacement is equal to 5 meters. Now you have to be careful when you write your direction here. This 37 degrees is here. This one is connected to the south, right? South, right? So first you're going to write S for south, then your 37 degrees, and then your second direction, which is west. Yeah, west. So, like that. And that is the displacement to that question. Not so hard. Go do some stuff like that. Rock on.